Today, we're going to start a new unit on stoichiometry, and it's really closely related to moles, but it's not exactly the same. We're adding an extra step, if you will, because you'll remember with our mole town conversions, we were essentially using, we were relating moles to grams to molecules, but we're adding a new step. So, stoichiometry is the use of coefficients in a balanced chemical equation. So, coefficients, those are the numbers out in front, as mole ratios to quantitatively analyze a reaction. In other words, we're going to analyze quantities or amounts of things that react and are produced using the coefficients as mole ratios. So, we're going to keep things real simple to start with. We're going to consider the following example. Let's say you have a job at Chick-fil-A, and your job is to make a Chick-fil-A chicken sandwich. The recipe is really simple. You take a bun, which is split in two. You take a piece of chicken, and you take two pickles, and you put them together, and you get one sandwich. So if I asked you, how many sandwiches could you make if you had 12 buns? Well, you could make 12 sandwiches because it's a 1-to-1 ratio. If I asked you how many sandwiches you could make if you had 20 pickles, well, since it takes two pickles for one sandwich, you're going to need twice as many pickles as you get sandwiches. So you're going to make 10 sandwiches from 20 pickles. We will come back to this analogy a little bit later, but we're going to consider some examples. Now, the first step in any stoichiometry problem is to write a balanced chemical equation. So if we want to solve this problem, it says if 5 moles of potassium chloride react, how many moles of oxygen are needed? Well, this equation we have up here is not balanced because on the left side of the arrow, we have 2 oxygens, and on the right side, we've got 3. So we need to put a 3 here, a 2 there, and a 2 right there. So that is our balanced chemical equation, and what this means is when 2 potassium chlorides react with 3 oxygens, we get 2 potassium chlorates, or when 2 moles of potassium chloride react with 3 moles of oxygen, we get 2 moles of potassium chlorate. So, this problem says if 5 moles of potassium chloride react, so we're starting with 5 moles of KCl, how many moles of oxygen are needed? Well, we're essentially going to be adding a new process to mole town. Because right now, you're familiar with, we've got moles, we've got particles, and we've got grams. And the relationship is between moles and grams. We have the molar mass. That's the numbers off the periodic table. And between moles and particles, we have Avogadro's number. Well, this is all if we're dealing with the same substance. We'll call it substance A. We could do the exact same thing. We could have particles of substance B, moles of substance B, and grams of substance B, where they're related by the same thing. But we have a new connection or a new bridge between moles of one thing and moles of another, which is our coefficients in a balanced equation. That'll let us go from moles of one substance to moles of another. So, if we look at this problem where we are starting with moles of potassium chloride, we can go from moles of KCl to moles of oxygen and use the coefficients where there are 2 KCl's and 3 oxygens. And that will get us to moles of oxygen. And when we set this up, our units will cancel. We have moles of potassium chloride cancel with moles of potassium chloride. And so 5 times 3 divided by 2 is 7.5 moles of oxygen. So that is a very simple stoichiometry problem. If you follow this process, there's never more than 3 steps to get from any one thing to any other thing on here. Sometimes there's only 2 steps. Sometimes there's just 1 step if we're going between moles and moles. But the basic process, if you want this summarized in individual steps as opposed to a graphic organizer, step 1 is convert to moles. Step 2 is to switch compounds using your coefficients. And step 3 is to switch to the units the problem asks for. Because your first step, if you're not starting in moles, is you've got to get to moles. Then you switch compounds using your coefficients. And then if it doesn't want moles as an answer, if it wants particles or grams, switch back to those units. So for those of you who don't like graphic organizers like Moletown here, you can just use those 3 steps. So let's look at sample problem number 2. It says how many grams of potassium chlorate are produced from 17 moles of oxygen, right? Well, we are starting in moles of oxygen and we're trying to find grams of potassium chlorate. So we're starting with moles of one thing, we're trying to find grams of another. So we're going to switch compounds and then convert to grams. So our first step is we need to switch from moles of oxygen. Since we're already in the unit of moles, we can make the switch. We need to go from moles of oxygen that the problem starts us with to moles of potassium chlorate. And we can do this using the coefficients. The ratio, it is a 3-to-2 ratio where 3 moles of oxygen make 2 moles of potassium chlorate. When we set up this conversion, whatever units we start with need to appear on the bottom of our conversion so that the units will cancel out. And then oxygen has a 3, potassium chlorate has a 2 in front of it. So that's where we get the numbers, and that's how we get everything set up just right. The second step is to convert into grams because the problem wants to know an answer in grams. So we need to go from moles of KClO3 to grams of KClO3. Once again, since we had moles here on top to start with, they move to the bottom. Our conversion from moles to grams is that 1 mole of potassium chlorate equals the mass of potassium, 39.1, plus the mass of chlorine, 35.45, plus the mass of oxygen, 16 times 3. Put that into a calculator, it comes out to be 122.55 grams. And then we've got everything set up so that our units will cancel. And it'll give us an answer in grams of potassium chlorate. So we take 17 times 2 over 3 times 122.55 over 1, and we get 1,300 388.9 grams of potassium chlorate. All right, so let's try this whole thing with a different reaction. Let's consider the combustion of butane. So we have C4H10 plus oxygen makes carbon dioxide and water. I balanced it with a 2, a 13, an 8, and a 10. This is a combustion reaction. So the first question says if 1 mole of C4H10 reacts, so we're starting with 1 mole of C4H10, it wants to know how many moles of CO2 are produced. We're already in the unit of moles, so we can switch compounds. We can go from moles of C4H10 into what it wants us to find, which is carbon dioxide. We check our reaction. There's a 2 in front of C4H10. There's an 8 in front of carbon dioxide. So then we just plug these numbers into a calculator. 1 times 8 divided by 2 equals 4 moles of carbon dioxide. And that's a very simple problem. It's just one step going from moles of one thing to moles of another using our coefficients. Now we're going to look at a problem that's as complicated as it can possibly get. If 5.7 times 10 to the 24th oxygen molecules react, how many grams of carbon dioxide are formed? So we're starting with 5.7 times 10 to the 24th molecules of O2, and we're trying to get to grams of CO2. Well, our first step is we need to go from molecules, which is particles, into moles. Then we're going to go from moles of one thing to moles of the other, and then we're going to switch into grams. In other words, we convert to moles, we switch compounds, then we switch to the units the problem asks for, which is grams. So our first step, we got to get to moles. So we need to go from molecules of O2 to moles of O2, where 1 mole equals 6.022 times 10 to the 23rd. It's Avogadro's number. The second step, we can switch compounds because we started with oxygen. The problem wants us to know about carbon dioxide. So we're going to use the numbers in front of oxygen and carbon dioxide, the 13 and the 8. That's our stoichiometry step. And then we need to get our moles of CO2 into grams of CO2, where 1 mole equals the mass of carbon plus the mass of oxygen times 2, which is 44.01. We've now got this problem set up where all of our units will cancel. Molecules of oxygen cancels with molecules of oxygen. Moles of oxygen and moles of oxygen cancel. Moles of carbon dioxide and moles of carbon dioxide cancel, leaving us with an answer that will be in the units of grams of CO2. And if we plug these numbers into the calculator, we get 256.35 grams of carbon dioxide. So I want to give you a few precautions. First, write out all of your steps. Don't just try to do this in your head on a calculator. Put it down on paper. Second, don't try to be doing shortcuts and not writing your units. If you write your units and you set it up where whatever units you have on top move to the bottom of your subsequent conversion until whatever's on top is what the problem asks for, or in this case, just a single step, this will help you avoid making simple mistakes. Also, I award partial credit on tests if you show your work and I can tell where you made your simple mistakes. If I can't tell, I just have to count the whole problem as incorrect. So take your time, write it out on some paper, show your work, be careful.